Hi, Algebra 2 friends. Here we are in Chapter 10, and we're looking at Section 10.1, Exponential Functions. Our vocabulary today starts with exponential function, and an exponential function looks like this: y equals a times b to the x, or of course, function notation, f of x equals a times b to the x power. And a can be any value aside from 0, and b must be greater than 0 and also cannot equal 1. If you think about it, 1 to any power will just be 1, and so we'd actually end up with a horizontal line, if you could think about that. All right, so one thing that we need to know, or a few things that we need to know, is that exponential functions can look, when we graph them, a number of ways. And right now I'm going to show you examples of exponential growth, where we increase as we go to the right, and exponential decay, where we decrease as we go to the right. So in exponential growth, as x increases, y or f of x increases. And in decay, as x increases, y decreases. So what do these equations look like? Well, the equations for exponential growth functions are going to look just like these guys, right? However, the b term, let me use a different color here, the b term will be greater than 1. All right, so when the b term is greater than 1, when I'm taking a number that is greater than 1 and I'm raising the power over and over again, that's going to give me an increase. However, when I take the number b, or this value, and this number is somewhere between 0 and 1, if you think for a moment, you'll realize those numbers are fractions. And if I multiply a fraction over and over and over again, which is what an exponent will do, I'm going to get a decrease. So that's how we can kind of differentiate between the two types of exponential functions. An exponential equation is going to look something like this. You've got like 3 to the x minus 4, and that's equal to something like 27 to the 1 over x power. And you are going to be in a place where you'll understand how to solve for that x value. So that's what an exponential equation can look like. And an exponential inequality is going to be similar, where you have the variable. Notice the variable x is in the place of an exponent, and you might be comparing it to something like 1 over 256, and you need to solve for x in terms of the fact that this is an inequality. All right. Our first example here asks us to graph this particular exponential function. And I know you guys can pull up any kind of graphing device and graph it using technology. I do think that there is something about graphing by hand that kind of helps you have a better knowledge of what's going on. So we're going to graph this by hand, right? So here's what we're going to do. We're going to choose some numbers. Let's go from -2 all the way up to maybe +3, something like that. And let's plug in some values. So when we take 2 and we raise it to the -2 power, what we are going to get is, if you remember, negative exponents makes us take the reciprocal. So 2 to the second power is 4, but 2 to the negative second power is 1/4. And if we continue with that line of thinking, we'll realize that this will also give me a fraction. But when I take 2 and I raise it to the 0 power, I get 1. When I take 2 and raise it to the first power, I get 2. You know the deal, guys. I know you know how to do this. And so here are my values, and now I'm going to plot them. So at -2, this is 1, we're at +1/4, so we're close to the x-axis. Here we're right here, because we're at 1/2. We cross through the 1 on the y-axis. 1's going to give us 2, and you can see we've got this 2 increase. 2's going to give us 4, 3's going to give us 8, and we have this kind of a function here. And so that's what our graph looks like. All right? And what we really should observe here that's really important is that if I continue on to negative infinity, doesn't matter how small these numbers are, if I get further and further negative, I'm going to get smaller and smaller numbers for my y value, but I won't get 0, and I won't get a negative value. And so what we'll realize is that we get closer and closer to the x-axis. We realize that exponential functions are oftentimes asymptotic with one of the axes, or asymptotic horizontally. Sometimes we can shift these graphs around. But yeah, so there's an asymptote at y equals 0. So that's something we need to look at and talk about. Also notice that oftentimes, as long as the a value, and the a value here is 1, remember our equation is in the form a times b to the x. In this case, b is 2, a is 1, as it is not depicted there. As long as a is 1, no matter what we take b and raise it to the 0 power, we will get 1. So as long as a is 1, we're going to pass through 1 on the y-axis here, all right? So a couple things you want to observe. So now let's get to the domain and range. So the domain will be all real values, all reals. And we can write that in a number of ways. We can say anything from negative infinity to infinity would be all reals. So that would be one way to write the domain in that kind of notation. And another way, interval notation, and another way would be to talk about, we could just write all reals. But in terms of the range, rather, we can see that the range is a little bit different. We're never going to get a negative number, nor will we ever get y equaling 0. But y can be pretty much any number greater than 0. So our range, if we continue with this interval notation, is going to be from 0. This parentheses means I'm not including 0, all the way out to infinity. So that's going to be our range. Any y such that y is within this interval. So if you remember what we talked about last time, if we have an exponential function, it's of this form, and you remember that b had certain restrictions, and b's restrictions are going to influence whether we have growth or decay. So we know that if we have growth, b has to be greater than 1. If we have decay, b is going to be less than 1 but greater than 0, because b must be greater than 0, must be positive. So determine whether each represents growth or decay. Clearly, since this number is less than 1 but greater than 0, we have a decay here. Okay. The next one, if we have this function, will this be growth or decay? And since we have a 4 there, that's greater than 1, so we have growth. And finally, even though 1.2 isn't much greater than 1, it is, and therefore there is growth here as well, even if it's slow growth. So in your textbooks, if you look at this example, you'll see that there's a little bit more explanation, but the explanation basically is the same thing that we just talked about. So if you prefer to have a picture of this, I'm going to put this up for you so you could see it. Here in example 3, we're to write an exponential function. So in 1983, there were 102,000 farms in Minnesota, but by 1998, this number had dropped to 80,000. So the first thing we're going to do in part A is to write an exponential function of the form y equals a times b to the x. That could be used to model the farm population y of Minnesota. We're going to write the function in terms of x, where the x is the number of years since 1983. What this tells us is that 1983 is 0. So what I want you to see is that we have two ordered pairs here that actually should satisfy an exponential function. So the first one, recognizing that we're talking about time since 1983, 0 is 1983. So in the 0th year, we had, or 1983, we had 102 farms in Minnesota. But a few years later, and the question is how many years later? Looks like 15 years later, this number dropped to 80,000. So we would be putting a 15 here to reference that next bit of information. So in 1998, the number was 80,000. So now what we're going to do is try to use these 2 points to come up with an equation that is specific to this situation. So the first thing is, anytime you have a 0 point with a point that has x, or well, I should say, this would be the y-intercept. I don't know if you can think about that, because we have 0 for x and we have a y value. So anytime you have the y-intercept, that's super huge when you're dealing with an exponential function. So watch this. I know that y is equal to 102,000 when we're dealing with x equaling 0. And so since x is equal to 0, we know b to the first power, to the 0th power must be 1, and therefore this is a times 1 is equal to this number. So you guys know what we just got. We got the value a. So we know our equation is y is equal to 102,000 times b to the x. So that's so far so good. The next value we need to get is b. And in order to find b, we're going to be using this next point. How we'll do that is like this. We're going to take the 80,000, put it right in there for y, and then we're going to figure out what b is by taking the 15 and putting it in for x. So what you notice is that the only variable here is b, which is great because that's what we need. So we're going to divide both sides by 102,000, and when we do that, the right side is simply b to the 15th power is equal to this fraction. So how do we undo this? Well, if you remember, we undo a fraction by taking the nth root. We undo a power like this by taking the nth root. And in this case, we need to take the 15th root. We can do that by raising this to the 1/15th power. What I do to one side, I do to the other. I'm definitely going to plug this into a calculator. So now I've got b to the 15th raised to the 1/15th is just going to be b to the first, b by itself. Next, I'm going to take this fraction 80,000 over 102,000 and raise that to the 1/15th power. I'm going to use my calculator. I get approximately 0.9836. So what does my equation look like overall? I know this is a whole lot of stuff, guys, but stay with me. My equation is y